So all science, including physics, is based on making measurements, and all measurements therefore require units. Units are really important. You want to make sure that in every problem you include the unit and that you use the right unit. And in addition, that you're using the same units throughout the whole problem. For example, you don't want to have miles in one part of a problem and then meters in another part of the problem. You need to convert, so it's all miles or all meters. And in general, what we want to do is we want to convert everything to what's called the SI system. The standard SI unit of time is seconds. So if you have a time given in any other unit, generally the first thing that you want to do is to convert that to seconds. Now, formally, 1 second is defined as the time required for 9,192,631,770 oscillations of the radio wave absorbed by cesium-133 atom. So that's a very, very specific definition. You do not have to remember that definition. What you need to remember is that if you are given a time in minutes, hours, days, whatever, you almost always need to convert that to seconds first. The standard SI unit of length is the meter. So in most cases, we're going to convert from whatever length units you're given to meters in the beginning of a problem. Meter is defined in a similarly complicated way as second. It's the distance traveled by light in a vacuum during 1,299,292,458th of a second. The SI unit of mass is called the kilogram. The kilogram is defined as the mass of a standard kilogram, which is made out of platinum, iridium blend, and it's stored in Paris. And so all other kilograms are compared to that, and that's considered the gold standard. So generally, you want to always convert to kilograms. Now, that one's a little bit different. Notice that meters and seconds are the base unit, but kilogram is not. Gram would be the base unit for that, for the mass measurement, but kilogram is the standard unit that we're always going to use. So instead of converting to grams, you always want to convert to kilograms. When we're using the SI system, there are many prefixes that you can use to change units really easily. Kilo is one of those. So kilogram means that you have 10 to the power of 3 grams. Some other common ones are milligrams, which is 10 to the power of -3, and centigrams, which is 10 to the -2. In some cases, we may use micro and nano as well. We won't usually use giga and mega. That's going to be a little bit more rare. It's very important to be able to convert back and forth between SI units and other units, as well as between SI units like grams to kilograms. Here are some other useful unit conversions that are going to commonly occur in this class. So you may want to write these down, remember them. You can also look them up in the textbook. This is table 1.4. So how do we convert between units? There are several different methods that you might want to use. The easiest way is to set up a series of ratios. So for example, if we wanted to convert from feet into meters, we would start with 2 feet, and we're going to multiply that by 12 inches over 1 foot so that the feet will cancel each other out. Then we're going to multiply that by 2.54 centimeters over 1 inch. That's how many centimeters there are in 1 inch. We do that so that now the inches will cancel out. And then finally, we're going to convert from centimeters to meters. So in every 1 centimeter, there's 10 to the -2 meters. We get that from our chart on the previous slide. Now the centimeters are going to cancel out, and the unit we're left with is meters. So that gives us that 2 feet is equal to 0.610 meters. The last step in any problem solving is to assess your answer, to make sure whether or not your final answer makes sense. And this is very important in converting units. It's easy to make a mistake, to write your ratio upside down, so you want to always make sure that it makes sense. For example, if you're working a problem about automobile speeds and you reach an answer of 35 meters per second, how close is that? Is that a reasonable answer or not? Well, here are some rough conversion factors. 1 meter per second, as we see in the chart, is actually 2.24 miles per hour. But if we just say it's about 2 miles per hour, we can say that 35 meters per second is somewhere around 20 miles per hour. We have a better intuition for miles per hour than we do meters per second. So while you may think, I don't know how fast 35 meters per second is, 20 miles per hour, you have a good idea of what speed that is, and that's a reasonable answer. In contrast, if you had reached an answer of 350 meters per second, you know that you did something wrong. The last thing we're going to talk about here are significant figures. It's important in science and engineering to be specific about how much you actually know. So, for example, if you report the length of something as 6.2 meters, what you're implying is that that's all you know about the measurement. That you know the actual value is somewhere between 6.15 and 6.25, so you rounded it to 6.2. If you've actually measured it much more accurately and you know that it's 6.217, then you should record that many significant figures so that the precision of your measurement is shown in the number that you write down. So 6.2 would have two significant figures. More precise measurements, as I said, will give you more significant figures. So the appropriate number of significant figures is then determined by whatever data you have when you're making real measurements. Most of the problems in our book will either have 2 or 3 significant figures. When you do calculations with significant figures, they all follow what's called the weakest link rule. So the input value with the smallest number of significant figures determines the number of significant figures to use for the output. So if one of your input values has 4 and one only has 2, then your answer should only have 2. It defaults to whichever is the smallest. So let's look at an example here. How many significant figures does this number right here have? Well, these 3 in the beginning don't count. If they're before the first non-zero digit, they're not significant. They're just placeholders. They're just telling you what place these digits are in. Anything that's not 0 is automatically significant, which means the 6 and the 2 are significant. And if we have another 0 to the right of that 6 and 2, then, and it's past the decimal, then that's also significant. So in this case, how many significant figures does this one have? 3. 6, 2, and 0 are all significant. On this slide, I'm going to summarize the rules for using significant figures in calculation. So when multiplying or dividing, taking a square root or anything like that, the number of significant figures in the answer should match the number of sig figs in the least precisely known number used in the calculation. It's a little bit different for adding or subtracting. For adding or subtracting, we go with the number of decimal places, not the number of significant figures. So when adding or subtracting several numbers, the number of decimal places in the answer should match the smallest number of decimal places, not necessarily the smallest number of significant figures. Importantly, exact numbers do not affect the number of significant figures. So for example, if you're multiplying something by 2 or you're multiplying something by 4, you wouldn't default to one significant figure. Those exact numbers that you're multiplying by don't affect the number of significant figures, only in the measurement values that you put in. It's also a good idea to keep at least one extra significant figure until the last step. Even 2 is a good idea, but definitely 1. The reason for this is that if you round off every time to the number of sig figs that you want to have in the end, you're going to accumulate errors, especially if there are multiple steps in the problem. So it's a good idea to keep 1 or 2 extra and then only round off once at the end. As I told you before, in this textbook, most problems will either be 2 or 3 significant figures, as the data for that particular situation requires. So again, let's look at a couple of examples. 1 multiplying and 1 adding. So if we want to multiply these two numbers together to calculate the mass of this second piece of aluminum, we would take the volume and multiply it by the density. So we were given the volume of 4.44 times 10 to the minus 4 meters cubed, and we're given the density of 2.7 times 10 to the third kilograms per meter cubed. Multiplying these together is going to tell us the mass. When we multiply these together, we get 1.199, but that has too many significant figures. How many significant figures are in our first measurement here? Should be 3. All 3 of those are significant because they're all non-zero numbers. How many are significant here? This should be 2. So how many significant figures should our answer have? it defaults to the lowest number. So the answer should just have two significant figures, meaning that we should round off 1.199 kilograms to 1.2 kilograms. And that's what you should report for the final answer. Now, to find the total mass, we need to add that to the mass of the first piece. So now we're looking at adding two measurements and not multiplying them. Adding, we default to the lowest number of decimal places, not significant figures. So in this case, 6.47 plus 1.2, this has two decimal places, this has one. So our answer also needs to have one decimal place. Meaning that even though when we add these together we get 7.67, we need to round that off to 7.7 so that it has the same number of decimal places as the starting number with the fewest decimal places. So let's finish up this lecture with a quick question. We're going to try to put in order from the most significant figures to the least, the number of significant figures in each of the following numbers. Some of them may be equal. So let's think about this for a minute. I'll give you a few minutes to look at it and see what you can come up with, and then we'll discuss it. So think about this for just a few seconds. Did you get an answer? Let's see if you were right. How many significant figures are in each of these numbers? In this one, there are 2. In this one, there are 2. In this one, there are 3. And in this one, there are 4. So which of these choices puts these in the right answer? D has the most significant figures, followed by C, followed by A and B, which are equal. So the correct answer to this question would be A. If you have any questions about any of this material or you need extra help with it, please come and see me and I'll be happy to help you. But you want to make sure that you understand this as we move forward in the class. This is just background information that everybody needs to be comfortable with before we proceed further into physics.